So welcome to the first active learning introduction of the semester. So what you're going to find is I'm going to do a short video recording showing you an example of the type of calculation that I'm going to ask you to do and to submit as an assignment. So let's talk today about electric force calculations. You'll have to do for the test either an electric force or an electric field calculation, so it's important that you know how to do these. So let's first of all start off by talking about Coulomb's law. Coulomb's law says that the force between two charges that are separated by a distance r is proportional to the two charges, and it's inversely proportional to the square of the distance between them. So F is equal to K Q1 Q2 over r squared, where K is a constant, and that constant K is equal to 1 over 4 pi epsilon naught, where epsilon naught is a very small number, 8.85 times 10 to the minus 12. It's the permittivity of free space. The unit for charge is a coulomb, and that proportionality constant K, if we put in what epsilon naught is just equal to 8.988 times 10 to the 9, and usually we'll just shorten that to be 9 times 10 to the 9 when we do our calculations. So 1 coulomb is a very, very large charge, and usually in the problems you'll see microcoulombs. Remember, micro is 10 to the minus 6, or nano, 10 to the minus 9, or sometimes even picocoulombs, which is 10 to the minus 12 coulombs. Now remember, forces add up like vectors from physics 1, so superposition of forces just says if you've got more than one charge, the net force on a charge is equal to the sum of the vectors of the forces from all the other charges. So if you look in the picture down below, that pink charge in the top left-hand corner feels a force on it due to all the other three charges there, and the net force will be the vector sum of those forces. The direction of the net force will depend on which force is bigger. So if I look at this picture here, if I look at that small charge, negative Q, over here on the right-hand side, it's going to be repelled by the negative charge and attracted by the positive charge. So remember, the force between two like charges is repulsive, and between opposite charges is attractive. So there's going to be a force from the positive charge to the left. There's going to be a force from the negative charge to the right. Which one of them is going to win? Well, it depends on which one is bigger. And remember, the distance, the force is KQ1, Q2 over r squared. So the Q's are the same, but the r's are different. The negative charge is closer to the charge on the right side than the positive charges, so the negative charge is going to have a bigger force. So the negative charge is going to have a larger force, so I can draw that as a larger arrow. And so there's going to be a net repulsive force. So the net force on that little charge is going to be over towards the right. So that's a one-dimensional. What if we have a two-dimensional case? So now I've got that positive charge there that's up at the top of the triangle. What direction is the net force on it? Well, again, force is K Q1 Q2 over r squared. So I've got equal charges down here. I've got equal directions, so equal distances, because this is an equilateral triangle. So r is the same. So those forces are going to be the same size as each other. What about the directions? Well, between the positive charge and the positive charge, that's going to be repulsive. So that force up at the top is going to get repelled away from the positive charge at the bottom, and it's going to get attracted down towards the negative charge at the bottom. So I've got two equal forces, one that goes up and to the left, and one that goes down and to the left. So if I add those two together, I'm going to have one vector going like this, another vector going like that. The net sum of them, remember, if you add two vectors, the resultant goes from the tail of the first to the tip of the second. So the resultant vector is going to go over towards the right. So the answer is going to be D. Okay, what if I have a square of charges? What's the direction of the net force on the charge at the lower left? A, B, C, or D? Well, again, think about the net forces. So it's going to be, so what you do when you do this is you think about which is the charge that's moving, and then imagine you put a nail through all these other charges so they can't move. The only one that can move is the one that you're thinking of. So the one in the bottom left corner is going to get pushed away from all the other positive charges. Okay. So it's going to get pushed down by the one at the top left. It's going to get pushed to the left by the one at the bottom right. So a force in the direction of A, a force in the direction of C, and there's also going to be a force in the direction of B. So if I add all those three together, where's it going to be? Well, it's going to be, these two are equal size, so that'll add up to a diagonal, plus I've got the diagonal one. So all those three vectors are going to add together to give me a diagonal force downwards and to the left. Make sure you know how to do conceptual questions like this with directions of net forces. All right, so to add vectors, we're going to have to use trigonometry. So let's really quickly review what we learned back in high school and then again back in Physics 1. Remember, if you have a right angle triangle, the sine of that angle theta that we have down there in the bottom corner, the sine is opposite over hypotenuse, so it's going to be A over C. The cosine is the side adjacent, the side that's touching the angle over the hypotenuse, so B over C. Tangent is opposite over adjacent, it's sine over cosine. And Pythagoras' theorem tells us that A squared plus B squared equals C squared. All right, so if we're going to solve a problem, we need to use that rule, F equals KQ1 Q2 over R squared. First, draw a picture, put in arrows for all the forces to make sure we know the directions. Then calculate the magnitude of each force. And by magnitude, I mean absolute value. So ignore any directions given by having a negative charge or a positive charge. Just use your arrows for directions. Break the forces into components. Add the components together to get the net force components, and then combine those components to get the magnitude and the direction of the net force. And if you remember from Physics 1, we use those two equations there at the bottom. You add the x component and the y component squared, so vx squared plus vy squared gives you the total length of the vector. And to get the direction, we use the fact that the tan of theta is vy over vx. Okay, so let's switch over now to my whiteboard and let's work on a problem. So here I've got 4 charges arranged in a square. I've got the charge for each one given there in microcoulombs, and the sides of the square are 0.1 meters long. So it asks us what's the net force on Q4. That's the charge down in the bottom corner here. Okay, so we're going to follow the instructions. So first we're going to draw a picture. We're going to put on arrows for the forces. So, and let's label the forces with subscripts so we know what they are. So I've got Q1 is negative, Q2 is positive, Q3 is positive, and Q4 is positive. So that'll tell us about the direction. So what's the direction of the force between Q1 and Q4? Well, they're opposite signs, so Q4 is going to get attracted towards Q1. So that's force 1, 4. All right, how about between Q3 and Q4? Well, they're both positive, so Q4 is going to get, let me erase that, that's not very nice. It's going to go straight over towards the left, force 2, 4. And then force 3, 4, between 3 and 4. The force between 2 and 4, they're both positive, so that's also going to be repulsive, and that's going to be down in that direction. Okay, what else do we know? We know the sides of the square are 0.10 meters, so it's 0.10 meters between there and there, and there and there, and between there and there. All right, so I've drawn a picture. I drew my arrows on there. Next thing is to calculate the magnitude of each force. So to calculate the magnitude of each force, I'm going to use just that equation. So force equals K Q1 Q2 over R squared. So let's do the force between 1 and 4. It's going to be K Q1 Q4 divided by the distance between 1 and 4 squared. All right, so K is 9 times 10 to the 9. Q1 is negative 10 microcoulombs. So that's negative 10, and micro is times 10 to the minus 6. Now I said to calculate the magnitude. So when I calculate the magnitude, I'm going to just completely ignore the fact that I had a negative sign there. So I'm just going to calculate 10 to the minus 6. Okay. And then Q4 is 2 microcoulombs, 2 times 10 to the minus 6. Okay. And then what's the distance between them? Well, the distance between them is just one side of the square. So that's going to be 0.1 meter. And don't forget to square that. So if I put all that into my calculator, I get that the force is 18 newtons. What's the direction? The direction is all along the plus y direction. Okay. Now I can do the same thing for the force between, let's do it between 3 and 4. That's an easy one because it's right along the edge. So I'm going to have K Q3 Q4 over the distance between R3 and R4 squared. Okay, so 9 times 10 to the 9 times Q3. Q3 is 5 microcoulombs. Again, micro is 10 to the minus 6. Q4 is 2 microcoulombs. Again, 2 times 10 to the minus 6. The distance between them is 0.1 meters squared. And when I put my numbers in there, I get 9 newtons. And that's in the minus x direction. So I did the two easiest ones first. Let's now do the tougher one. And the tougher one is only tougher because I have to figure out what's the distance, the diagonal distance between 2 and 4. Okay, so the force between 2 and 4 is going to be K Q2 Q4 over the distance between 2 and 4 squared. So that's 9 times 10 to the 9. Q2 is 10 microcoulombs. 10 times 10 to the minus 6. Q4 is still 2 microcoulombs. And now I need to know what's the distance between, diagonal distance between 2 and 4. Well, if I look at the square, all right, so I want to know the diagonal distance. I know each side is 0.1. So the distance between 2 and 4, the diagonal distance on that square, we can just use Pythagoras. So 0.1 squared plus 0.1 squared. So R24 squared is equal to 0.1 squared plus 0.1 squared. Okay, so that's 0.141 squared. Okay, so 0.141 squared. And so I get that it is again, 9 newtons. And it's diagonally. So it's going to have part in the x direction and part in the y direction. And it's going to have part towards the negative x and part towards the negative y. All right, so we've done step 1. We drew the picture. Step 2, we calculate the magnitude of each force. Now we need to break each force into components. So what I like to do is, let me pull this up. I like to make myself a little chart with the x components and the y components for each vector. So let's start again with the easy ones. Okay, so 1, 4, force 1, 4 is all in the plus y direction. So it's got 0 in the x direction, and everything, the whole 18 newtons, is in the plus y direction. Force 3, 4, that's all in the minus x direction. So it's got minus 9 newtons in the minus x direction, 0 in the y direction. And now force 2, 4, I have to break that up into a component in the x direction and a component in the y direction. So if I draw my vector, it's 9 newtons and it's diagonal of a square. So those angles are 45 degrees. Okay, so the x component is going to be the side that's horizontal. So this is going to be F24x. And the y component is going to be the vertical side. Okay, so if I let's use this angle in the bottom corner. The x component is adjacent to the angle. It's touching the angle, so that means I'm going to use cosine. So it's going to be 9 cosine 45. And the y component is then going to be 9 sine of 45. It's opposite. And if you look at the direction of the vector, it's going the negative x direction and the negative y direction. So I'm going to throw a negative sign in front of them. Okay, so 9 cosine of 45 is 6.364, and 9 sine of 45 is also minus 6.364 because the sine and the cosine of 45 degrees are the same as each other. All right, so I've done step 3, broken the forces into components, and then we add the components to get the components of the net force. So to get the net force in the x direction, all I do is I add up my numbers down the x column. So I've got minus 9 and then minus 6.364. So that's minus 15.364 newtons. In the y direction, I add up the y, so I've got plus 18 and then minus 6.364. And that gives me plus 11.636 newtons. Okay, so there's my net force components. And now I've got my components, I can find the magnitude and the direction. How do I find the magnitude and direction? Well, if I scroll back up, I use these two equations in yellow down here. The magnitude is the sum of the x component squared plus the y component squared. The direction we get by using the tan of the y over the x. All right, so the net force is going to be square root of f net x squared plus f net y squared. So it's going to be square root of 15.364 squared plus 11.636 squared Why did I get rid of the negative sign? Well, when I square the negative sign for the minus 15.364, it's going to become positive. And for some of you guys, I know your calculators don't function properly. They don't actually take the square of the negative and make it positive. So it's safer just to drop it. All right, so when I do that, I get 19.27 newtons. And remember, we should always make sure for our final numbers we're consistent with the significant figures. Looks like I've got 2 significant figures maybe on my problem. So let's round that to 19 newtons. What's the direction? Well, for the direction, tan theta is y over x. So it's going to be F net y over F net x. So that's going to be 11.636 over negative 15.364. And that gives me negative 0.757. How do I get the angle from that? Well, theta is going to be the inverse tan, the arctan, whatever you want to call it, of 0.757. Sorry, negative 0.757. And so it gives me minus 37.14 degrees. So what does that even mean, that negative angle? Well, to figure out what it means, I have to draw a picture of my actual vector. So if I draw a picture of my vector, let me see, let me go over onto the side here. So my actual net force vector, it goes backwards 15 in the x direction. So I don't know, let me assume those are 5s. And it goes up 10 in the y direction. So back 15 point something, up 11 point something. So it's something like that. So the vector goes, there's my net force vector. Okay, so my angle that it gave me an angle of 37 degrees. What angle looks like 37 degrees in that picture? Well, probably that one in there. So the fact that it gave me a negative number for my angle is completely misleading. Okay, so that angle there is 37.14 degrees above the negative x direction. So when you're putting this problem in the homework service, they want to know what's the angle from the plus x direction. So I have to actually, to give the right angle, I have to calculate the angle between the plus x direction and the vector. So the angle should be 180 minus 37.14, which is 142.9 degrees. And usually I would say above the plus x. So it's important for you to always draw the vector so that you know when your calculator gives you an angle, that you know what that angle actually means, which quadrant is the vector in, so you know what the number is. Okay, so what do I want you to do with that? Well, what I want you to do now is to go online and upload your solution to the following problem. So you've got these 3 charges in an equilateral triangle. The sides of the triangle are 1 centimeter in length. And in an equilateral triangle, all the angles are all 60 degrees. I want to know what's the magnitude and direction of the net electric force on charge 1, which is the charge in the bottom left corner. Okay, so make sure when you do this, you need to put your charges into coulombs. They're nanocoulombs, 10 to the minus 9. And you need to put your distances into meters. And you notice here it's given in centimeters.